Okay, so I'll point out here, you can see the triple point of CO2 at 5 atmospheres and negative 56 degrees Celsius. What's cool, what's interesting, what I want to use to discuss this supercritical fluid point, right? Check it out. So again, this is TC and PC. It's pretty convenient where this occurs, and convenient meaning these are conditions that are easy to reproduce in a laboratory. 31 degrees Celsius and 73 atmospheres, that's fairly convenient to reproduce. So quick math, 73 atmospheres is about 1,000 pounds per square inch. When you buy a cylinder of carbon dioxide, they're often filled with 2,000 pounds per square inch. Okay, so getting the critical point and thus creating supercritical CO2 is pretty convenient. And there are a lot of amazing things you can do with supercritical CO2. So I have a video that I'm going to share with you all. I'm not going to play the full video, but I did add this to our playlist and on my YouTube channel. And what I'm going to point out here, so I'll just kind of describe what this guy's got going on. He's got a chamber and it's filled with liquid CO2 as well as gaseous CO2. So you can see here that liquid line right there. That's the liquid, and above that liquid is vapor, is CO2 gas, right? And you can see right there he's got a thermocouple in there. So right now this chamber is 24 degrees Celsius. It's really hard to see what the pressure is on that scale, but it's sufficiently large that he's going to be able to make the supercritical CO2. Okay, and so watch what happens as he heats this up. This is really cool.
CO2 is starting to boil in there.
Temperature's going up. Watch what happens at 31 or 32 or so, you guys. It's really cool.
Okay, now the boiling has pretty much stopped. You can still see some density changes in the liquid there, but at this point there's no more bubbles, and the transition from the liquid to the gas phase in there is almost gone.
Oh, and look, the pressure's going up. I saw the scale go up. Look at that. The boundary is gone.
And as you can see, something interesting has happened. There's no more dividing line between liquid and gas inside there.
Cool stuff.
So I'm going to unplug the heater.
So I can't remember how long it takes him to drop it down back below, but we'll watch for a few minutes.
Cloudiness to subside.
So you can see it's cooling down.
What we're left with here is one phase basically inside the chamber. The CO2 has gone supercritical, meaning that the density between the liquid phase and the gas phase eventually became so similar that they blended together. So it's all one continuous phase in there now. Now to transition back, what I'm going to use is just a piece of dry ice, and I'm going to hold it against the
more CO2
aluminum on the outside here to bring the temperature down quickly. So check this out. Surprisingly, this actually works better with just water ice, since it melts and makes a nice contact between the aluminum and the ice cube.
There you go. Back to liquid CO2.
Back to two phases.
Okay, so that is really, really awesome. It's not cool because it's actually 31 degrees Celsius, right? So what can you do with supercritical CO2? So some of you already know the answer to this, and you probably are thinking, I can extract marijuana, and that's right, you can. Or you can extract THC from marijuana using supercritical CO2. There's also a lot of other things that you can extract out of material with supercritical CO2. And the reason for that is it becomes an ideal solvent for organic molecules when it's a supercritical fluid. So in other words, it has the same density, right? The liquid and the gas have the same density and this makes it extremely viscous. Okay, so if you have some other organic material, like a plant or a flower, right? This supercritical fluid can actually penetrate, through like the cellulose and through those structures of the plant, and actually dissolve the material that's inside there, particularly, let's say, the THC in the case of cannabis. You can also extract flavonoids and flavor molecules from other types of materials. So people do a lot of supercritical CO2 extraction on hops and barley to get certain molecules out that they want. And of course, you can't tell it, I only want this molecule to be extracted out. You get everything out of there, right? When you put some organic material into a supercritical CO2 chamber, it's going to pull out everything. So you then from there have to use your organic chemistry skills to separate all of those compounds that you pulled out by the boiling points. So I actually did some of this in grad school. I didn't do this on cannabis, but I did this on natural materials. We use supercritical CO2 to extract fatty acids out of soybeans. And we did this actually for a class. I didn't do it for my research. It was for PChem lab, which I was the grad student TA of. But it was a mess. It turns soybeans into just an organic, soupy mess. But it is very cool. You can run that stuff on a mass spec or a GCMS, separate out all the materials based on their boiling points. So supercritical CO2 is a really cool industrial material for solvents. It's a wonderful solvent for organic material. Okay, so the next one I want to talk about, helium. This one is very cool, as it turns out. So you notice, right, like 2, 3, 4, 5, 6 Kelvin, cool. Okay, so here the triple point at helium occurs a shade above 2 Kelvin and at a pretty easy vacuum to achieve in the lab. But now you notice there's this interesting thing called a lambda line. I'll get more into what that lambda line means in the next coming lectures. But what you have at that lambda line, and check this out, right at 1 bar, that's roughly atmospheric pressure. It's right there, okay? And on the other side of that, it's a superfluid. So just warmer than 2 Kelvin, it's just regular old liquid helium. So what is a superfluid? Okay, what he's really getting at is this this canonical ensemble idea that literally every atom is the same. That is in contrast to what Boltzmann says. Boltzmann says there's a distribution of these energies or these temperatures, right? There should be some average value, okay? But this material, it's become so cold, there's no longer a population of states. You could think of this as it's got one microstate as a superfluid, okay? And there are some amazing consequences as a result. Check it out. And so also to describe, he's got that little glass capsule that you see there, that also contains helium, and he's going to do something cool where he pulls it out of the liquid and you'll see what happens. So what's happening there? Let me elaborate on that. It's a solid piece of glass on the bottom, okay? But a superfluid has no viscosity, none. So what that means is there's no friction between the individual atoms, and there's no friction between the atoms and the container. So there's no more adhesive or cohesive forces. And any teeny tiny nanometer sized defects in the glass are now places where that superfluid can just pass right through. I'm serious. It can just pass right through the glass as if it weren't even there. Pretty amazing stuff. Pretty amazing stuff. So there's tons of videos out there on supercritical CO2 as well as helium as a superfluid. If this inspired you, you'll find a ton of awesome videos on those two things. And I would encourage you to explore that. So I think that's all that I wanted to do with this lecture. I wanted to keep it nice and qualitative. So the next one, there will be math. Okay, folks, I'll see you later.